Okay, so number 5, we were just about to start. So it's an engineer developing a new type of gun that someday can launch satellites. One such gun can give a small object a velocity of 3,500 meters per second through only 2 centimeters. Okay, so most times if you fire a bullet or launch a satellite, the VI is going to be 0. And that 3,500 is going to be its final speed after they've put a force on it to accelerate it over this distance of 2 centimeters. So delta D is 2 centimeters, which of course has to be changed to meters, and there's 100 meters in a centimeter, so this will be 0.02 meters. And so the question wants to know, what will the acceleration be? So again, what equation do we have that has a VF, a VI, and an A at delta D? It's the same one again. I need to mix this sheet up. We've been using this VF squared equals VI squared plus 2A delta D for the last 4 questions. This time we're rearranging for A. So again, bring your VI squared over, and actually it goes to 0. So you can even just cancel it out right away, and then you don't even have to take it over. We want the A by itself, so divide by the 2 and the delta D, and that will be A. So then fill in your numbers. A will equal 3,500 meters per second squared over 2 times 0.02 meters. Clearly this is going to be tiny. So 3,500 squared divided by 0.04 should give you something crazy like 3.0625. 3.0625 times 10 to the, put it in scientific notation, 8 meters per second squared. Okay, so that's a huge acceleration. It's not lasting over a very long distance, but it's huge. Now the second part of the question says over what time period does this happen? So you have A, you have VF, you have VI. I would probably use for part B, A is equal to VF minus VI over delta T, because it'll be easier than using the big equation delta D equals VI delta T. So rearrange for delta T. Delta T will be equal to VF minus VI over A, and remember VI was 0. So delta T is equal to 3,500 meters per second divided by 3.0625 times 10 to the 8th meters per second squared. So this time it's going to be minusculely tiny. So take the answer that you have and divide it into 3,500. You get 1.143. 1.143, it's really 285, times 10 to the negative 5. Negative 5 seconds. All right, number 5, done. Number 6, a car initially sliding backwards down a hill at negative 25 kilometers per hour. So our VI, so negative, it's because it's going backwards, right? So for number 6, our VI is negative 25 kilometers per hour. The driver guns the car. By the time the car's velocity is positive 35 kilometers per hour, so the final velocity 35 kilometers per hour in the other direction, it has traveled 200 meters. Delta D is 200 meters. Assuming uniform acceleration, what was it? So you're looking for A. So the first thing you have to do is change your 25 and your 35 kilometers per hour into meters per second. And so we do this by dividing by 3.6 as our shortcut. We already did the conversion factors. So this one is 6.94 with the 4 repeating. And remember, it's a negative. And 35 divided by 3.6 is going to be almost 10. 9.72 with the 2 repeating. All right, and so we want our A. We have VF, VI, and delta D again. It's going to be VF squared again. So VF squared is equal to VI squared plus 2a delta d. And we're looking for a, nothing goes to 0, so vf squared minus vi squared is equal to 2a delta d, and then divide both sides by the 2 and the delta d. So vf squared minus vi squared over 2 delta d. And no, you don't have to show me this in between step if you can do it all in one. I just don't want to mess anybody up. So it's going to be 9.72 repeating meters per second, and that gets squared, minus a minus 6.94 meters per second squared, divided by 2 times 200 meters. Okay? A equals. So try to keep the repeatings there when you square them so you don't end up rounding too much. So square the first one, subtract, square the second one, and obviously the negative is going to disappear inside the bracket but not outside. So on the top you should get something like 46.296, etc. meters squared per second squared after you subtract them, divided by 400 meters. Oh, I screwed something up. Oh, it goes 3.2 meters, not 200 meters. I must have looked at a different question. This is 3.2 meters. I was going to say that's a really tiny acceleration. This is not 400. This is 6.4 meters. So if I multiply this by 400 and then divide by 6.4, then you get, that's better, 7.234. 7.234 meters per second squared. Okay? And then the last one that I asked you to do last night, number 7, says, highway safety engineers build soft barriers so cars hitting them will slow down at a safe rate. As mentioned above, a person wearing a seatbelt can withstand an acceleration of negative 300 meters per second squared. How thick should the barrier be? How thick is going to be delta D? How thick should the barrier be to safely stop a car, VF is 0, that hits the barrier going 110 kilometers per hour? So that's your VI. So switch your 110 kilometers per hour into meters per second, and it should be 30.5 repeating meters per second. What equation do we want? We have an A, a VF, a VI, and a delta D. It's going to be VF squared is equal to VI squared plus 2A delta D again. Rearranging for delta D, VF squared minus VI squared, divide by the 2A. So delta D is going to equal, VF goes to 0, minus your 30.5 repeating squared over 2 times negative 300. Delta D equals, so square your 30.5 repeating with the repeatings divided by 600, and you should get 1.556 meters. 0.556 meters. Okay, now the soft barriers they're talking about, you've probably seen the like the yellow buckets around the base of the bridges, and those yellow buckets are filled with sand so that when you hit them, they're not as hard as the concrete that the pillars of the bridge are with. Speaking of cars hitting things, tomorrow I need to give you the car crash essay sheet that I've had since the first day of school. Okay, so don't let me forget to give it to you tomorrow. All right, next up, new thing. Not really new, but free-falling objects.